Hello and welcome. This is Dr. Schleif, and in this video, I'm going to be explaining how to collect the data that we like to use to analyze the acceleration of planet Earth. So this is the JUMP lab. All right, the JUMP lab involves measuring 3 different displacements corresponding to 3 different positions of a human jumper on planet Earth. Forgive my crudely drawn representations of a human being. So this is a human being in what we're going to call squat position. And what we need to do is measure from the ground to the center of mass of the human being. The center of mass for humans tends to be around the belly button. So let's call this displacement 1. We'll use S for displacement, and that's going to be the first measurement. So your lab partner is going to, squat down, and you're going to measure from their belly button to the floor. And then the next position, I mentioned to students before I started recording, let me give credit where credit is due. This lab is inspired by a lab, Defy Gravity, in the active physics textbook, okay? And so if this sounds familiar to you because you've worked through the active physics textbook, this is the inspiration for this lab. So we're going to call this one here ready position. All right, in ready position, you've yet to leave the Earth. You almost have to do like a fake jump, a faux jump, if you will, to go from squat position up to ready position. All right, but don't leave the Earth yet, because you want to give your lab partners a chance to sort of spy, where is your belly button there? Okay, and we're going to call that one S2. All right, so that displacement is how far from the ground is your belly button when you're like standing up as if you were going to jump, but you haven't quite jumped yet, right? So there's no way to jump without like bending your knees or you're like flexing your ankles, right? You have to convert some stored elastic potential energy in your legs into energy of motion, okay? And along the way, you've got to do a squat. Like there's no way to jump without doing a squat first. The third position that we're going to consider, we're going to call that peak position. And this is where you've left off of the Earth. And now your displacement S3 is, again, from your belly button down to the ground, but you're at the top of your jump. We're going to call that peak position. Okay, so squat position, ready position, and peak position. I think it might be called this jump position. I don't know, whatever. And now let's think through, if we measure these 3 displacements, I should have drawn this smaller, maybe this bigger, so that you could see like this is the smallest, right? They're getting longer from left to right there, but they almost look the same here. Right, so from your belly button to the ground, S1, belly button to the ground in ready position, S2, and belly button to the ground in peak position, S3. 3 displacements that you're going to record, so 3 lengths. You can start to brainstorm how you could measure that accurately using like rulers taped to the wall behind the jumper, or by recording it and trying to sort of look at the, the recording in slow motion or whatever. So, but they're distances that we need to measure, S1, S2, and S3. All right. Let's start at peak position. In peak position, you've got some potential energy due to gravity up there, okay? So one of the first things that we're going to sort of calculate once we've collected this data, all right? So the data table is going to be, well, one thing we're going to need to know is the mass of the jumper. So the mass of the jumper in kilograms. Here's where I tell everybody in class that you may not want to publish your mass. It's related to your weight, and that might be a private thing that you don't want to write down in your journal and have everybody sort of, read about and know about. So you're not required to jump. No one has to jump. You just need to be in a group of people where there's at least one jumper. And if you're in a group of lab partners where no one wants to jump, no one wants to publish their mass, then I volunteer to be your jumper, right? Because I don't mind telling you all that I'm about 100 kilograms of mass. I'm actually more than that, but I'm gonna lose some weight before we do this jump lab. The goal is to be able to slam dunk a basketball, right? And so one of the things that we'll realize is that here at peak position, you've got some potential energy due to gravity equal to your weight mg times the height. This was the equation that we derived yesterday from the work done in lifting something. H here, though, is going to be the difference between S1 and S3, right? Because it's sort of like this is our zero. We're starting out here. Our mass sort of starts here at S1, right? We're not starting at the ground. But that's what we're measuring it to because it's a nice, consistent sort of zero, right? So let's rewrite this slightly and say that we're going to do this here on Earth, okay? We're not doing the slab on the moon or anything, not yet anyway. Haven't got that field trip budget approved yet. So your weight is your mass times G, that's your weight in newtons, and H here is going to be what? S3 minus S1. So we'll be able to calculate how much potential energy your body possesses at peak position. Energy is neither created nor destroyed, all right? So we're sort of realizing that all the energy that you possess in peak position came from elastic potential energy stored in your leg muscles when you were in squat position. So we could sort of equate all this energy was energy stored in your legs, sort of here. But you do some work in lifting your body. In other words, you've got some potential energy here relative to this. And there's two ways to think about this. We could say, well, let's calculate the potential energy again at this position, S2 minus S1. But that's also like saying, what's the work that I do in squatting? Okay, you do work when you do a squat, right? You're lifting. So let's think about what work is. Work done squatting equals force times displacement, right? In general, work is force times displacement. The force that you have to exert to do a squat is your weight, mg. And the displacement that you undergo is going to be the difference between S2 and S1, right? So you're sort of lifting yourself from S1 up to S2 there. And that's like a height too. In other words, it's the height that you have sort of relative to this. And so it's exactly the same equation. This is a different way to think about it. Remember, we derived this equation from the general definition of work done. So this is going to be your weight mg times the displacement here, which is just going to be S2 minus S1. Here, all of your energy is elastic potential energy. Here, all of your energy is gravitational potential energy. But along the way, some of that energy gets spent sort of work done squatting, or there's a mix between kinetic and potential energy when you're in ready position. So what we want to do is subtract away the work done squatting, which is also equal to like the potential energy, the little bit of potential energy that you've gained from here to here. If all you do in the weight room is a squat, you never jump, you never do a jumping squat, you're just moving your weight up and down, right, from squat position to ready position, right? You never leave the earth. You don't exert enough force to actually leave the ground with some velocity v. What we want to be able to do is reason our way to get that velocity. With what velocity do I leave the earth with that gravity slows me down eventually to a stop when I'm at peak position, all right? So if we take our potential energy due to gravity and we subtract away the potential energy due to gravity at peak position, okay, and we subtract away the potential energy that we have here, which is, again, equal to the work done squatting. So we're going to subtract away, the work done squatting. Then there's an energy budget that we're sort of keeping track of here. We're accounting for some missing energy. Some of the energy goes into squatting. There's extra energy above and beyond that, kinetic energy that allows us to leave the earth, right, with some velocity v, and then we get sort of slowed down there. And so if we subtract away the work done squatting from all the energy we possess here, the difference between those must have been the kinetic energy that we possessed upon leaving the earth, right? So we're going to be able to deduce our kinetic energy just using an energy conservation argument. That energy had to come from somewhere, and if we account for the work done squatting or the potential energy we have from here to here, subtract it away from our total energy here, then all the rest of it must have been kinetic energy. That's sort of the thinking there. And we know an equation for kinetic energy. So if we remember that kinetic energy is equal to 1/2 mass times velocity squared, and we already know the mass of the jumper from way back when, then we'll know this number we'll know the mass, and we'll be able to solve for v. All right, so we'll know what velocity did we leave the Earth with. All right. Now, once we know velocity, we could think about our acceleration. We had to accelerate from a speed of 0 up to that speed over a time t, right? Acceleration is the rate of change of velocity. We could try to measure this time directly, right? You could try to like time how long does it take a person to go from squat to ready position with a stopwatch, or even better, record it and use the time signature. That's a pretty accurate way maybe to get this time. But I can think of another way to deduce the time using an equation of motion. You may recall that displacement equals 1/2 initial velocity plus final velocity times time. This is one of the equations of motion that we derived a few weeks ago. If we start out at an initial speed of 0 here, and we end at our final speed v that we can calculate from energy, then we'll know v, we know u, we want to know t, so that we can say, well, how much time did it take us to accelerate from 0 up to that speed? Like we have that speed right when we leave the Earth, right here. So the displacement is the same displacement as our squat, right? This S2 minus S1. So if we had S2 minus S1, that's our displacement. We could multiply that by 2 to get rid of that half. And we could divide each side by v. Remember, this is 0, so we don't really care about that either. Divide each side by v, and now we've solved for t that way, from things that we can sort of measure, or we've already measured, we've already calculated. That's enough now to calculate the acceleration. It's going to be our speed v minus the initial velocity 0 over this time here that we calculate from our displacement squatting. That's going to give us acceleration. That's how much we accelerate. We know from Newton's second law that force equals mass times acceleration. So as soon as we know our acceleration, we know our mass still, we could calculate the resultant force, or the net force that's required to lift us up off of the Earth. Like, what force did we use to actually leave the Earth with? And then we can use Newton's third law to realize that forces exist in pairs, right, between two objects. The two objects interacting here are the Earth, right, and the jumper. So this force is going to be the same force that accelerates the Earth, but the Earth is just a lot more massive than the jumper. Okay, so the force is one and the same, but the masses are very different. The goal for this lab, the jump lab, is to answer the question, how much can I accelerate Earth? Earth is going to accelerate you, but because of Newton's third law, you're also going to accelerate the Earth. Now, let me say this. We're making an assumption here that isn't valid because it's kind of all we can do. We're assuming that Earth is a rigid sphere, okay? And that means that it's going to move all together as one object. It's a rigid sphere that moves together as one object. Earth is actually a planet with like dirt and mud and lava and water and lots of stuff that will get squashed together. Like when you jump, the whole Earth doesn't move underneath your feet. Some of the molecules directly underneath your feet kind of get squashed together a little bit, and you never really move the whole Earth. So we are saying, well, let's just assume that the entire planet Earth, with a mass of 5.97 by 10 to the 24 kilograms, that is the mass of planet Earth, is all going to move together. So once you know how much force you've exerted on the Earth, you just say, oh, that's the same force that Earth pushed back up on me with, right? I push down on the Earth pushes back up on me, and Earth must accelerate also. But when you plug in the inertia, the mass of planet Earth, you'll realize that it hardly accelerates at all, right? Like that's such a big number. There's such a tendency to resist change in motion, so much inertia, that while it's calculable, you'd never be able to measure it directly. And again, it doesn't even really happen that way because the Earth just sort of, squashes down underneath your feet a little bit. It doesn't really move altogether. So as a quick recap, let's remind ourselves what we're doing with the jump lab. Answering the question, how much can I accelerate the Earth, right? Beginning with the end in mind. So you're solving sort of for this. The acceleration of planet Earth is going to be the force that you push down on the Earth with, the equal and opposite force it pushes up on you with, you push down on it with, divided by the mass of planet Earth, which thanks to Henry Cavendish's famous experiment, 5.97 by 10 to the 24, right? Henry Cavendish did the experiment to determine the universal gravitational constant, and they called that weighing the Earth, right? Because as soon as we knew that, we could figure out the mass of planet Earth. So your lab partner starts in squat position, and you measure the distance from the floor to their belly button. They do a faux jump, a fake jump, like they were going to jump, but they don't actually leave the Earth, just so you can measure how high above the Earth is their belly button if they were to jump in ready position. And then they actually do the jump, being consistent here. And consistency is going to be key, because I'm going to throw in another little wrinkle into this lab right now. I could just measure this directly. I could have you all stand on a forced platform and just jump on that forced platform, and I'll measure your jump force directly. And so I'll tell you to be consistent, because that's how I'm going to check your lab work. You all are going to deduce the acceleration of Earth, get the force from these displacement measurements, but then I'll have you replicate your jump identically. Okay, you have to replicate it identically, because if you're off, if you jump harder or with less force, then it's going to hurt your grade. Okay, you have to be consistent with your jump here. I like how people on YouTube might think, wow, that's like the most harsh physics teacher in the world, but hopefully my students know that I'm joking about that. But just, try to be consistent as you can. And the idea would be we could corroborate our conclusions here with something that we, another way to measure it, just like we always like to do. Okay. So we can't actually measure this directly, but we're going to sort of use Newton's laws to sort of practice with that together. All right. So at your peak position, your gravitational potential energy, mgh, subtract away the work that you do squatting, which is your weight mg times the displacement, S2 minus S1, right? That's how much displacement you've undergone there. Once you subtract away the work you've done squatting from all your potential energy in your peak position, the difference is the kinetic energy that you left the Earth with, which we could relate to the equation 1/2 mv squared. Solve for v. Once you know v, you could plug it in here with your change in position from S2 to S1, right? Which is a way to calculate how much time it took you to accelerate that, from 0 to that speed. And then we can calculate the acceleration from that. Once we know acceleration, we could use F equals ma to get the force. Newton's third law tells us that the forces are one and the same. Jumper on Earth, Earth on jumper. And because we know the mass of the Earth, we could calculate the answer to our question, how much can I accelerate the Earth? Right? So there's a lot of physics that goes into this, but really lots of energy conservation, right? But it's also a way to sort of remind ourselves of our equations of motion and how we can sort of be clever thinking through a lab. If you have any questions about this, just leave it down in the comments below. I'll be happy to field those questions with a follow-up video. This has been Dr. Schleif explaining the jump lab, and we'll see you next time.